going to use. When do we use conversion factors? Unit 1, where we're doing, your numerators and your denominators, and you're canceling out your units. So if that was not your thing back then, this is going to be your thing now. Okay, the second time around, most people really the light bulb goes off, and you start to see how the units relate to each other. Okay, so we're going to go through some new conversion factors. Now, here's the 3 new ones. This is not on your notes right now. Probably in like 2 slides, 3 slides, it'll be on your notes. So you can write in the back of that sheet if you want. You can write in your notebook. I don't care. So the first one is Avogadro's constant. By the way, started grading. My nomenclature's looking pretty good on a lot of us. I got a lot of hundreds, or close to 100 on the first slide, and on the back side on Lewis structures. It just takes me a long time to grade some of these. But a lot of you guys got 90 pluses on the multiple choice, which was really nice. So, yay! All right, Avogadro's number, Avogadro's constant is 6.022 times 10 to the 23rd particles. Particles per 1 mole of those same particles. Okay, so particles can be lots of different things, and I'm going to emphasize what they are in the next slide. So I know I'm going to hold you in suspense for just a little bit here. So if I wanted you to get a mole of carbon, you would go pick up 6.022 times 10 to the 23rd atoms of carbon. That would be, you'd be doing that forever, but that's one of the conversion factors. And of course, conversion factors go either way. You can write them top or bottom. The numbers don't switch. The numbers, 1 mole of particles and 6.022 times 10 to the 23rd particles, that's just literally an equivalent, okay? They equal 1 because they are equivalent to each other. Like 1 dozen is equal to 12. That's an equivalency. Next one, that's the second conversion factor we're learning, is molar mass. What 2 units do you think are involved with this one? Moles and mass, right? It's not lying to you, it's what it says. Moles of something and mass of something. So what you do is, it's always 1 mole, okay? So 1 mole of something, let's go dinosaurs, okay? 1 mole of dinosaurs is going to weigh some number of grams of all those dinosaurs together, okay? So it's whatever you're talking about, you add up its mass. You can find the mass, though. The mass is really, really, really easy to find. Where have you seen masses before? Right. Normally, you're going to be going straight to the periodic table to find these masses. Okay, the first one, it's in your head. Avogadro's number, you memorize. You keep it in your head. But you'll accidentally memorize it because you'll use it a lot today. Molar mass you find from the periodic table. Molar volume of a gas. This one is a standard conversion factor only at STP. STP, what did that stand for? Standard temperature and pressure, right. So we're going to talk about what these are, 1 atmosphere and 273 Kelvin. We'll see that again on this couple slides from here. Molar volume is only about a gas, okay? Only gases. Gases, are they close together or far apart from each other? Far apart. So it takes up, one molecule of gas being, a foot away from another molecule of gas, let's say. 6.022 times 10 to the 23rd of those babies would take up so much space, okay? Because they're just far apart from each other naturally. So 22.4 liters is how much space 1 mole of gas takes up. So 2 liters, about yay big, yeah? 2 liters times 11. Okay, that's how much 1 mole of gas looks like. You see it? You can see the gas. Get your gas X-ray vision out. Okay. So those are 3 new conversion factors. Notice everything is 1 mole. 1 mole is equal to a certain number of particles. 1 mole is equal to a certain mass, or 1 mole is equal to certain liters of gas. It's always 1 mole. That is a key fact. Okay, so this is not in your paper yet. So we just talked about this a little bit, but I have a couple of examples that I want to go through with you. So this is like an SI unit. This is a system of international measurement. So everybody uses the mole in sciences, okay? So the definition is 1 mole will allow us to convert between moles and representative particles. All right, representative particles represent a specific subset of chemicals. There are 3 specific subsets of chemicals. Sodium chloride, what subset of chemicals am I referring to? What kind of compound? Ionic. Okay. So if I say carbon dioxide, covalent, and if I say iron, it's just it's an atom or it's an element, okay? So it's elemental state. So the three representative particles are these, and I'll talk through these as I go. Write down what you need to, but I'm going to talk through them and kind of give you a diagram here. So the first type of representative particle is an atom. An atom represents some sort of elemental chemical, just straight from the PTOE. Atoms of oxygen, atoms of copper, atoms of iron, atoms of neon, atoms of argon. Just something straight from the PTOE. The second one is a molecule. So a molecule, molecular, did that refer to ionic or covalent compounds? Covalent, because a molecule is nominal together. My best example is carbon dioxide. Everybody knows what carbon dioxide is. It's nominal, it's covalent. So it's only referring to covalent compounds. If you say molecule, you're telling me it's covalent. The third representative particle is a formula unit, and that's only if you're referring to ionic compounds. So this right here that I've just written is essentially summarizing the stuff below. The only thing I've not added is the quick review of the type of molecules we talked about. Our diatomic molecules. What does that look like on the periodic table? H plus 7, right? Big 7 in hydrogen. So the diatomic molecules are H2, name them off in the 7 order. What's the first one? N2, O2, F2. Hold on, I'm almost there. Just gotta scroll down. Oh. Yeah. Okay. F2, Cl2, Br2, and I2. Yeah. So it's a big 7 in hydrogen. Those are your diatomics, and those would be molecules of hydrogen, molecules of chlorine, molecules of iodine. Not atoms. That's the big differentiation here, because though, yeah, they're from the periodic table, they are, they're locked together as a molecule form. They're not atoms here. All right, so let's look at some pictures. Let's see what these things look like, and then we'll get into some math. I know some of you guys are math happy. So, first one, neon, atom, molecule, or formula unit? Atom, because it's just straight from the periodic table. H2 gas, molecule. Name this. This right here. NH42Cr2O7. Dichromate. Yay. Okay. Ammonium dichromate is that big feature here. That's a formula unit. That's a structure. So this right here, ammonium dichromate. I'm saying I have 1 mole of that. 1 mole of that weighs 252 grams. Okay. I'm making, what's that? It's not, you can't say just something 8 if it's not an ion. So it doesn't have a charge on it. This is a compound. No. Chromium what? Chromium what? 3 oxide, or chromium 3 oxide. Because that 3 belongs to chromium, that 2 belongs to oxygen. Chromium is a transition metal. Okay, so that's chromium 3 oxide. 1 mole of that, so 6.022 times 10 to the 23rd formula units of that weighs 152 grams. So the grammages can be different. That's because they weigh differently. There's like a ton of different elements in that one. There's only 2 different elements in this one. So they weigh differently. But if I counted up all the ammonium dichromates in here, I would find 6.022 times 10 to the 23rd of them. Because it's just how many are there, making the other things. And this is a molecule of nitrogen, and these are 4 molecules of water. Okay, so you got to be able to use your language. Okay, do not write this down. This is me telling you, and you agreeing with me, that we are not going to use AMUs anymore. How do you mass atomic mass units? My scales, what did they mass in? Grams. I don't have a scale that masses in atomic mass units. Pretty much nobody does, okay? But atoms being so tiny, we know they are not measured in grams. Like I can go pick up 1 atom of carbon and say this is a gram of carbon. There's no way. Okay? That's going to be 1 atomic unit or 12 atomic units of carbon, but what really is an atomic unit? It relates to grams, but there's a conversion for that. And we don't really care about the conversion. We just care that we're going to say everything we're talking about now, we're going to talk in grammage form and not AMU form. So this is what this is referring to. The mass of 1 mole of any compound or element is the molar mass. We just talked about that. It's numerically equivalent to the atomic mass, AMUs, on the periodic table. So it's saying it's equivalent. So let's just say, never deal with AMUs anymore, deal with grams. And this right here says the same. It tells you why. But we don't really care why. We just want to do the problems. We want to know how to do the problems. Sometimes you just have to agree with me, okay? Let's agree to disagree. Okay. So this is on your paper. So if I say sulfur, I say I want 1 mole of sulfur. Periodic table says, what's the gram of 1 mole of sulfur? Grams, mass, 1 mole of sulfur? How are you getting that mess? You're just looking at the atomic mass, right? You just know how to use the periodic table. So periodic table, look for sulfur, say it's 32.06 grams. Truly, it's 32.06 AMUs, but we can't mass them out. We don't deal with the AMUs very well. So we're saying it's equivalent to grams. Okay, so iron, 55.8. What is the significance of 55.8 for iron? Let's have your periodic tables out. This right here is on your notes. What's up? Question?
I was saying it's not equivalent to grams. I was trying to see this.
Thanks. It's on the next slide. It's a confuser too, but we're not going to go to this. Okay, so this right here is on your periodic table. Iron, what's the significance of 55.8? That's its atomic mass, right? So if I say 55.8 grams of iron, you're going to tell me that's equivalent to 1 mole of iron. But my question is not about how many moles of iron this represents. It's saying how many atoms of iron does that represent? Yeah. Yeah. That equals 6.022 times 10 to the 23rd atoms of iron. Because if that's 1 mole of iron, then that means if I counted up all of the little atoms in that 55.8 grams, I would literally count 6.022 times 10 to the 23rd. These 3 things are equivalent. They're all equivalencies, and so we have conversion factors for them. Next, if I wanted 6.022 times 10 to the 23rd atoms of carbon, how would I get that if I had to mass it out? What would I mass? What's the mass? 12.01 grams of carbon. Because 12.01 grams of carbon is technically equivalent to 1 mole of carbon. And 1 mole of carbon is equivalent to, yep, 6.022 times 10 to the 23rd atoms of carbon. So all of these things are equivalent, yeah.
It's always the mass of 1 mole of that element?
Yes, that's what I'm saying. 1 mole is your key reference for moles, unless I tell you you're starting off with like 10 moles of something. That's when you get to write something other than 1 for moles. Okay, yeah.
What's the between MOL and MOLE?
Mole, so this is mole, and this is mole. Okay, those are both mole. This is just an abbreviated version of mole, one letter less, don't know why. But I sometimes write molecules like that. So if you ever see MOLE'(C), that's molecules, which is not a mole, okay? Just because I don't write molecules out all the time. Molecules, different than moles. Okay. So let's do the molar mass of more complex things. So yeah, you can find the molar mass of carbon and nitrogen. You just look on the periodic table, right? But we sometimes have to go out and calculate bigger masses. So I want you guys to do this one. How much you get? What's the name of that BT dubs? Pentoxide games. Okay, so nitrogen weighs what? 2 times nitrogen. Okay, so that's 14 each, right? Okay, plus 5 times oxygen. 16 each. What is it? Thank you. I was trying to do that in my head real fast. Okay, that's the molar mass. Molar mass you have to express as grams per mole. So I would write this as 108 grams of nitrogen dinitrogen pentoxide per 1 mole of dinitrogen pentoxide. That's truly what that means. That is equivalent to 1 mole of that. Now, not every single time do you need to write out dinitrogen pentoxide, especially if you're still talking about the same identity, like if you're comparing apples to apples all the time. But eventually, we're going to start comparing apples to oranges. So if you don't write the identity of what you're talking about, you might forget what you're talking about and think you could cancel it, but you couldn't. So I'm going to stay on the safe side and usually pretty much always write it, just because I'm an overachiever. So if you're with me, keep writing it. Okay, for this one, how would I calculate this one? Magnesium nitrate. So magnesium weighs what? 24.31. How many nitrogens are present? 2. Yes, there's a subscript out here. It distributes in. It says, not, I have a 1 right here after the nitrogen, but there's 2 nitrates, so that's NO3 and NO3 together, right? So I have 2 nitrates, so that's 2 times 14 for the nitrogen. How many oxygens are present? 6. So I'm saying 2 times 3. See, it looks like I'm multiplying them because there's a parentheses between them, and we're multiplying them, okay? So that's 6 times 16. I used to know these. That is 148.31. Somebody? Yay? Nay? Just agree with me. Okay, that's cool. 148.31 grams per mole. That is the molar mass of magnesium nitrate. Okay, so that's going to be helpful, especially when I'm asking for you to convert from moles of magnesium nitrate to grams of it, or vice versa. All right, so let's get into a little bit more. Oh, we got to do one more. We got to do volume. Skipping that one. Okay, so volume, that's the molar volume. So we just went through Avogadro's number. Now we just went through molar mass. Now we're going through molar volumes. There are 3 new conversion factors that we can tuck into our tool belt. So this is only for gases, because really, liquids and small amounts of solids, they have very negligible volume. There's not a big volume change. So we like to do this only with gases for now. And you kind of just wrote down some of this previously, but this defines standard temperature and pressure a little bit more. And I'm going to give you an example problem on here. This is the conversion factor. If that's all you write, that's it. 1 mole is equal to 22.4 liters. If that's all you write, that's cool. Gas, gas. So let's do what is the okay, my question is, what is the volume of 0.5 moles of carbon dioxide? So I'm going to give you a method on how to solve every problem. Please, please, please stick with it. Write it down. That way I can give you partial credit so I can actually understand what you're doing, okay? So first step is to identify the unknown. What's the unknown unit that I want? Volume. So what unit is that? Liters. I want to know liters. Question mark liters. Liters of what? Carbon dioxide. So I'm going to go specific here. I want liters of CO2. That's my true question. What is my given? What's my starting point? 0.5? 0.50 moles of CO2, carbon dioxide. I'm pretty much never going to write out a formula for you. I'm going to tell you names and you interpret formulas because you're a master's of nomenclature. If you're not yet, you will be soon because you'll kind of have to be because you'll get used to it some more. Okay, so 0.5 moles of carbon dioxide. So my third step is to use conversion factors to convert. So now conversion factors, I'm not going to tell you. You have 3 new ones. They are on your paper. Keep them in front of you until you get used to them. And then we can just start to kind of weed out, start to wean ourselves off of the paper. So moles of carbon dioxide. I want to get 2 liters of carbon dioxide. Is there a way to get directly from moles to liters? Yes, it's this one right here, right? So I'm going to put what on bottom? Bottom. Give me bottom first. Right, moles on bottom. So I'm cancel out moles. Who cares about moles? We want liters. So 1 mole of carbon dioxide goes on bottom, which is equivalent to liters of carbon dioxide. What's 22.4 divided by 2? 11.2. So 0.5 is divided by 2. Sometimes you don't need a calculator. It's overrated. 11.2 liters of carbon dioxide. Now, if you need to cancel those to see that. There you go. The only thing you're stuck with is a liter unit. That's the only one that's left. That's what we wanted. Yay, we won. Minis, you know, cheerleading stunts and stuff. That's what you do. CO2. Conversion factor. User conversion factor, sorry. I'm abbreviating. Yeah.
So it doesn't really matter what gas it is, half of the mole of any gas is 11.2.
Mhm. I can give you some crazy gases, but it's a gas. All gases approximately the same distance apart from each other. That's why. Like gas molecules. Yeah.
What is step one again?
Identify the unknown and write it down so that you can go at the end go, oh, I needed liters of carbon dioxide. Oh, yeah, I got it. It's just identification of your unknown. Yeah. Yes, sig figs, thank you. So 2 sig figs, 3 sig figs. This gets rounded to 11 liters. Good call. Okay, let's go do some real problems now. This is on your sheet. We're doing 1 through 6 together. 1 through 6 pretty much goes through every type of question I could ask you, and then you guys will do 1 through 8, okay? So write down these problems with me. I'm videoing too, so if you want to watch it again, then listen to me, but I think if you write it down, it's so much more helpful, okay? So these are not wordy problems, but eventually you'll get into wordy problems. So this one's easy to identify the unknown. What am I looking for? What am I looking for? I'm looking for what? Moles of what? Moles of silicon. Okay, I'm looking for moles of silicon. What's my given?
2.8
Atoms of silicon. Okay, that's my given. Now, we want to get from atoms to moles. Is there a conversion for that? There is. What is it? Avogadro's number, yeah. Okay, so I'm going to use Avogadro's number. Avogadro's number is what goes on top first. So what goes on top? What am I trying to get to? Moles. What number is always going to go with the mole? 1. 1 mole of silicon has times 10 to the 23rd atoms of silicon in it. So 1 mole of silicon is 6.22 times 10 to the 23rd atoms. So if you put this in your calculator wrong, your work will get credit, but your answer will not. Your calculator has no idea what you were multiplying by or dividing by unless you really are very explicit. You have this in parentheses in your calculator. 2.80 times 10 to the 24th, parentheses, divided by, parentheses, 6.022 times 10 to the 23rd, parentheses. If not, your calculator think in the end you're multiplying the whole shebang by 10 to the 23rd, and you're going to get the wrong answer. Here's what you get. 4.6496 moles of silicon. Sig figs. What's my lowest number of sig figs? Anybody? Where are you getting 2? There's not even one up there 2 in it. Yeah, this one's 3 sig figs. This one's 4 sig figs for me. So that's 3 sig figs. So this should be rounded to 4.65, right? So this is really awkward, but it's 4.649. So you need the first 3. So 4.64. The 9 rounds that 5 up. I mean that 4 up to 5. So 4.65 moles of silicon is our final answer. And that makes sense. I mean, 10 to the 24th divided by 10 to the 23rd, they essentially cancel each other out. So you shouldn't have like a humongous or a really, really small number afterwards. Okay, next. Identity. Question. Who are we looking for? What are we looking for? Grams of potassium, right. So we're looking for grams of potassium. Our starting point, 0.32 moles of potassium. Potassium is K, not P. I know it's tricky. Okay. Is there a way to get directly from moles to grams? Yes. What is it called? Molar mass. Where would you find such molar mass? Periodic table, right. You're not expected to memorize anything except for Avogadro's number and how to use it. But moles of potassium need to be gone, right? So 1 mole of potassium must go on bottom. What has to go on top? Grams of potassium, right? How many grams is potassium worth? 39.10. Okay, so moles cancel, yeah? Prove it to yourself, scratch them out. Only unit left, grams, score. Okay, so now we gotta calculate. What's like a third of 39? Like 13, 14? So 12.512 grams potassium, sig figs. What's my limiting sig fig here? Dose, round. They're 2 sig figs. Just these 2, but the 5 rounds the 2 up to 13. You get back into it. You just gotta get sig figs back in your forefront of your mind. You haven't seen them in a while. Okay, thumbs up so far, yes? One steppers. Okay, let's see if we have something that's a bit more than one step. Like, for example, number 3. Question. Atoms of oxygen. So now we're getting specific here. Looking for atoms of oxygen. I'm starting off with 1.14 moles of, what's the name of that? Sulfur trioxide, thank you. So it's a covalent compound, you must use prefixes. Okay, so I'm starting off with sulfur trioxide and going to just moles of oxygen. There's got to be a way to get out of a compound to a single atom, and we can do that. It's called a mole ratio, and it's internal, and I'll show you how this looks. So let's start off though, well no, actually we have to use that as first conversion factor, so let's go with this. Sulfur trioxide, if you had to draw this just skeleton structure, for like a Lewis structure, it would look kind of like that, you know, with dots and stuff around it, right? So obviously you can see it from a formula or from a structural formula, how many oxygens are in 1 mole of sulfur trioxide? 3, because there's, for every one of these, there's 3 oxygens within it. So that's called a ratio, and it's not sig figs, it's not a measurement, so there's no sig figs with this one, okay? It's just a simple ratio. So for every 1 mole of sulfur trioxide, within it, there are 3 moles of oxygen. This is just a ratio. That's not one of the sig figs that conversion factors I taught you, but that's just a new one I need you to kind of start to identify as needed. It's not going to be used on every problem. All right, so now we're to moles of oxygen. We're almost to atoms of oxygen. How would one get from moles of oxygen to atoms of oxygen? Which are those 3 new ones we learned today? Avogadro's number, right? It's not molar mass. It's not molar volume, so it's got to be Avogadro's number, right? So what goes on bottom? 1 mole. The 3 does not transfer down. It's just the fact that you're trying to cancel moles of oxygen out, so 1 mole of oxygen goes on bottom, which is worth how many particles? 23rd atoms of oxygen. Okay? So remember, our particles come in 3 varieties. Atoms, if you're dealing with elements, molecules, or formula units, right? So we have 3. All right, I'll calculate this. You guys stand up and stretch. I have people sleeping, and I'm not going to help them afterwards. Control yourselves. Stand up, everybody. Go give somebody a hug or something. High five. High five. And another one. Stand up if you cannot stay up. I woke up this morning and snoozed my alarm for almost 45 minutes. I thought it was Saturday. I almost was not here today. So I'm with you. I hear you. I just didn't think it was Friday. I thought it was Saturday. So I was like, dang it, I forgot to turn my alarm off again for the weekend. And then it went off again. I was like, this is fishy. Why is my alarm going off again? It must be not Saturday. So, yeah, I woke up in a rush. If I need to wear a mustache the rest of class, I will. I'm not going to say it's comfortable, but I'm getting prepared for St. Patrick's Day. It looks awful, though. Then I was going to make it a unibrow, but I thought that would also be bad. So, I'll make it like that. It's like a fuzzy caterpillar.
Oh yeah.
Okay, Rapido, back to your seat. Back to your seat for me. I can get a water. Is that okay? Okay. You agreed. Okay, write down the answer for trace. How do you say question? How do you say pregunta? Preguntas trace. Okay, so this will make sense as well because look, we have a huge number on top, 10 to 23rd on top. Nothing on the denominators are going to even compare to that. So we're left with a very, very large number. And that makes sense. we've got over a mole, and we've got 3 times as many moles of oxygen in there. So we've got that times 10 to the 23rd. So we're going to have quite a few atoms of oxygen here. So logically, you can always go back to the logic of the math. Okay, so next one. Ooh, sodium phosphate. All right, so what's our question? Grams of what? What is sodium phosphate? I forgot. Mm-hmm.
3.
3.
E.
Good, stop, good. So, grams of sodium phosphate. So the nomenclature is going to haunt you for the rest of your life. We need to figure out from 4.52 times 10 to the negative 3 moles of sodium phosphate, how many grams that's worth. So, is there a way to go from moles to grams? Straight there. Yes. So, I'm going to kind of set it up. What goes on bottom? How many moles? 1. 1 mole of sodium phosphate has a mass, sodium phosphate, of what? How would I get that? I can't just think about it and get it. Gage, what are you doing right now? And adding them up? Goody. Okay, so you're summing all those pieces together to get the total mass of sodium phosphate. This is not one thing, it's multiple things. Good. Thanks, Gage. So 3 times 23, or 22.99 for sodium. You should be looking at your periodic table to make sure I'm right. 22.99 plus phosphorus is 30.97 plus 4 times 16 for oxygen. Total mass, and you don't have to write this out, okay? I'm doing this for your benefit. You do not have to write that out. You can just go straight to the calculator and plug it in if you trust your little fingers, because sometimes I have butterfingers, so I have to make sure I'm right with you guys. That should sum to 163.97. Yeah? Okay. So 163.97 grams of sodium phosphate. Sodium phosphate moles are gone. Sodium phosphate moles are gone. Grams are left. Is that what I wanted? Totally. And drum roll, 0.471 grams of sodium phosphate. Sig figs, yeah? We good? Yeah, good, Miss Emily. Thanks, guys. Okay, 3 sig figs there. And that makes sense. We have less than a mole of sodium phosphate. 1 whole mole weighs 163 grams. We've got 0.004-ish moles. So it's going to weigh a lot, very, very little. It's going to weigh less than 1. So that logically makes sense. All right, 2 more. Liters of carbon dioxide to atoms of oxygen. Are we good here? What's up? What's up? My periodic table, I have lots of sig figs on my periodic table. Don't worry about that. If we're off by just a little wiggle room, no worries. We're still 163, right? 164-ish, we're good. I just go through, I have a different periodic table than you guys, and I just have most of those memorized. Okay, so next one, carbon dioxide to atoms of oxygen. Question, atoms of oxygen. When you think atoms, you think particles, yes? Particles refer to what? Avogadro's number, right? So next we see that we're starting with 2.5 times 10 to the second liters of carbon dioxide. When you say liters, what comes to mind? The volume one, right? What's the volume one? 24.2 liters, and I should have said add STP here, but I didn't. Sorry, assume it's add STP here. Okay, so I'm starting with liters. I want to get rid of liters. It's the only way to get rid of liters. Which of those 3 conversion factors? The molar volume one, right? What goes on top? 1 mole of CO2, good, because you want to get 2 moles of CO2, which is a nice stepping stone, pretty much to get you anywhere. So moles are going to be seen pretty much all the time. Okay, so what goes on bottom? 22.4 liters of carbon dioxide. So liters of CO2 are gone. Next step, I'm not to atoms O yet. Previously, how did I get from a molecule to a component of its molecule? I did that ratio thing, right? So, in CO2, in 1 mole of CO2, how many moles of oxygen are in 1 mole of CO2? 2, because it's a ratio. This is saying for every thing of CO2, there's 2 oxygens in it, so it's a ratio within a compound. Not like a random conversion factor. It's literally just a ratio. We're going to talk about ratios a lot next week. Okay, so 2 moles of oxygen. Okay, still not done. Next step. Oh, sorry, moles of CO2 cancel. Okay, so now I'm in moles of O. I'm going to get rid of moles of O. So it goes on bottom, yeah? Okay, so 1 mole of oxygen is worth how many atoms of oxygen? 6.022 times 10 to the 23rd atoms of oxygen. So anytime you're going for moles to particles, you always use Avogadro's number. That is 1.34 times 10 to the 25th atoms of O. So in your calculator, I don't think you're going to have really any issues in terms of the funny business is to make sure you do 2.5 times 10 to the second in parentheses, and then divide by 22.4, and then multiply by 2, and then multiply again by 6.822 times 10 to the 23rd. So that makes sense because you have on the top in the numerator position 10 to the 23rd, so that times 10 to the second. What happens when you have exponents of the same base? What do you do to them? Add them, so that's how you get 10 to the 25th. And is there something wrong with this final answer? Sig figs, how many? 2, so 1.34. Okay, last one, formula units. So we haven't had a formula unit one yet. Okay, so what are we looking for? Grams of, what is that formula? I2, good. So lead 2, iodines of 1, crisscross charges. The only time you're putting Roman numerals is on what? Transition metals. But all transition metals? Except for zinc, silver, cadmium, right. Cadmium and zinc have a 2+, always, don't have to tell me, I know. And then silver's the number 1. Okay. Question, lead 2 iodide, starting with 1.91 times 10 to the 21st formula units of lead 2 iodide, okay? Tell me, what's next step? Is there a way to get 2 formula units directly to grams? Formula units directly to grams. It is. You tell me what it is. Maybe this is a 2 or 3 step one, right? So what's our stepping stone to get something else? Moles. So this one we have to go from formula units to moles, and then moles will get us to grams. So the first one, from formula units to moles, what comes to mind? Avogadro's number. I'm going to keep saying avocados too. So Avogadro's number, because that's a particle and that's a mole. And then to get from moles to mass, molar mass, yeah? Okay, so formula units go on top or bottom? Bottom. So formula units of lead 2 iodide. And I'm going to moles, 1 mole of lead 2 iodide. How many formula units are in a mole? 6.022 times 10 to the 23rd. And then, so formula units of lead go away. And then what's my next step? What goes on the bottom? Okay, so 1 mole of lead 2 iodide is how many grams of lead 2 iodide? Lead is like 207.2. Is that right? Iodine, is that right? 2, okay. Iodine's like 1. She might not know the molar mass. She might, I don't know. What is it, 120, what is it? 26.1? 9, okay. So 207 plus 100, or 253 or 4 is 461?
Yes.
You guys have that up in your head? 461.12 grams on my periodic table. So that right there pops up here. Can't reach that now. Okay, 461.12 grams. Everything cancels except for grams, and you wanted grams, right? Because you were at the top that you wanted it. So you should have 1.46 grams of lead to iodide. Yeah. Okay. So, we're going to continue to have fun. Oh, that didn't take that much time. Okay, you guys have 8 fun problems ahead of you. If you would like to work with a partner, yes, do so. Before I release you, I'm going to eventually put all the answers up, but you're responsible for 1 through 8, so make sure you check yourself with me too. Before I release you, I have a joke for you, okay? Jokes. So, guy walks into the kitchen where there's people that have drinks. I'm not going to say what the real thing is. He walks into this area where people have drinks, and he asks for a cup of H2O. Guy gives it to him. Then his friend walks in and he says, I want a cup of H2O too. Then he dies. Why? Because H2O2 is what? Hydrogen peroxide? Okay, I told you that because it's on your problem set. I just wanted to make sure you knew what hydrogen peroxide was. Hydrogen peroxide is H2O2. Okay? Alright, so you guys can work together. Don't go to the lab station because that's for a while. We'll get you later if you can today. So I'm saying like 25 minutes. Let's see where we are then, okay? What have you done?
Hear about oxygen's potassium safe.
No.
It went okay.
I wish we could say potassium oxygen though.
What?
I wish we could say potassium oxygen. It would KO, but I can't correct the joke. A-okay, I don't know. Because it's got to be potassium and then oxygen. These people who make up these jokes. Okay, so you guys have the